All right, so today we're moving on to our next unit, which, like I mentioned last unit, still actually covers the topic of triangles. So units 2, 3, and 4 are all triangle related. We, at the tail end of this unit, will throw in a couple more shapes, just briefly, with a process called dilation, making shapes grow or shrink based off of a focus point. Like we'll do a square or a trapezoid or something like that. But still, the main focus is triangles. And the main focus specifically in this unit is twofold. Congruence, which we've heard congruent used before, meaning equal or the same. And then we'll also look at similarity, meaning some things are the same, but other things are, oh, bad definition because I'm using the same word, similar. Consistently similar. And basically what we'll see there is we'll have two triangles. One is either a little bit bigger or a little bit smaller than the other. But I won't spoil any of that because that'll be Monday, I think. Because we're going to focus on congruence first. And I've split it up into 2 days because there's multiple ways to determine congruence. Now, on a side note, the main method we're going to focus on determining congruence is through the use of proofs. Now, maybe you've heard of those before. Sometimes people get a little nervous about them just because of the way they look. It's less solving and more describing. So, like I was saying, proofs are less work mathematically, meaning we're not going to necessarily be solving equations to prove that two triangles are congruent. It's more analytical, meaning here's what I see, and here's how I describe what I see. So it is a different approach than what we've seen so far in this class. I think they can have the potential to be a little bit fun. On the flip side, though, sometimes they're a little bit stressful because occasionally it'll feel like we're maybe over-explaining things, but that's usually the case. So that aside, we're going to see some proofs here in just a little bit. But first, throwing some definitions out there. First off, congruent triangles are triangles with both the same shape and size, which means that all corresponding parts, which are, well, there's only two types of corresponding parts, angles and sides, are congruent. Now that does not, just to kind of clarify, that does not mean that every side in one triangle is congruent to the other, because then you have an equilateral triangle, and we said that those are rather unique. No, instead we're saying that one side of a triangle is congruent to one side of another triangle. The second side is congruent to the second side. The third side is congruent to the third side. So it's kind of a pairing activity. Now, when triangles are congruent, we can write what's known as a congruency statement. Now, a couple things I'm going to highlight here because it's already written. So congruency statement, in order for it to be valid, you have to match all corresponding angles and sides. So the order that you write it, technically the order that you write the first one doesn't matter, but the order that you write the second one depends heavily on how you wrote the first one. So let me explain here. There is a congruency statement written for this diagram. And you'll notice that it is stating that triangle ABC is congruent to triangle DEF. Now, if I didn't have the diagram and all I had was the congruency statement, so long as it is a valid one, I know immediately that the first angle in that triangle A must correspond with the first angle in the second triangle D. So A and D would be congruent. B and E would be congruent. C and F would be congruent. Now, those are the easier of the two, the angles. The sides are a little bit trickier because now you're dealing with two letters. But the way you would do that is I usually work my way through left to right. AB would be congruent with side DE. BC would be congruent with side EF. And then the other one's kind of a stretch. AC would be congruent with DF. Now, if I look at the diagram, visually, that's sketched out for me. A corresponds with D, B corresponds with E, C corresponds with F because of the little arcs inside of them, telling me that they're congruent. Even though they're not in the same triangle, they're being given to us stating that they are congruent. Same with the sides. Any questions so far? Why are the lines like that? So it has to do with pairing. So the side AB, which has one hash mark on it, is congruent to side ED, which also has one hash mark on it. So it's a way to visually see that, oh, this side and this side are the same. This one and this one. It's kind of like a matching. Okay. So then next we have a little acronym here, CPCTC. Well, that stands for corresponding parts of congruent triangles are themselves congruent. So I've kind of already alluded to that. I said, if you have a congruency statement telling you that those two triangles are congruent, you can go through and pick out the congruent pairs of angles and the congruent pairs of sides, which is going to be our next task here in just a moment, once you guys have a chance to jot this down. So taking a look at number one, we're going to list all congruent angles and sides given a congruency statement. So we don't even see the triangles here, but we have been told that triangle JKL is congruent to triangle PQR. So like I said, I like to go with the angles and I like to kind of work my way left to right as I pair them up. So for example, angle J, which one would that be congruent with? P. What about angle K? Q. And angle L? R. So based off of the congruency statement we were given, we can state these three smaller congruency statements as a matter of fact. Now, like I said, the sides are a little bit trickier because you're pairing up two letters now, but I kind of just work my way through it carefully. So I'm going to do the first one and then you guys help me with what's congruent with it. So side JK would be congruent to PQ. KL congruent with QR. And then the last one I'm going to say is JL, which would be congruent with PR. Be careful. Sometimes it happens to me. It may happen to you. Sometimes I say the same side twice because I think it's different because I reversed it. But remember, side, let's say JL is the same as side LJ. I've just read it in reverse. Still describing the same side. So be careful, don't accidentally say the same one twice. Now, the last request on this problem is to write another valid congruency statement. There's nothing wrong with the one we have now, but what it's basically saying is I can mix up the order of the triangle, but it will obviously then change the order of the second triangle. So I'm going to test your guys' observation skills here. I'm going to say triangle LJK. What triangle is that congruent with?
RQB.
Almost. So if you look at the order in the first one, I went L, which is the third one, JK. So third, first, second. So I have to follow that same pattern, RPQ. It's kind of sly. I won't ask you to do that often, because if you can write one valid congruency statement, that should be sufficient. But it's a good exercise to kind of wrap your head around the pairing. So RPQ, and that's not the only one. I could say KJL and QPR, or JLK and PRQ. The list could go on, not forever, but long enough that it's going to be boring if we did all of them. So any questions with this one? We could say a lot without even having a diagram, so long as we have a valid congruency statement. Okay. Number two, same idea. I'm going to go a little bit faster just because it's more of the same. We're given that triangle WXY is congruent to triangle EFG, which tells me that angle W is congruent to angle E. Angle X is congruent to angle F, and angle Y is congruent to angle G. Then I work through my sides. WX is congruent to EF. XY is congruent to FG. And WY is congruent to EG. And then as for another valid congruency statement, again, as long as I just mix up the order just enough, maybe say triangle XWY. What would that be congruent with? FEG. So we're just making a bunch of statements so far. Not really anything to calculate or to measure or anything, just stating facts. So we'll try one more. This one's already been kind of laid out for us. We are told in the statement that triangle KPM is congruent to triangle AYC. Now, if you needed to, you could go in and draw in the little matching angle arcs to say which ones were congruent. Same with the sides. You're welcome to do that. You're not required to do that. What we need to do is go through and see if we can finish these following statements. So side KM, what is congruent to KM?
AC.
AC. What about side CY?
MP.
MP. PK?
AY.
Yes, you're not wrong, Misty, because AY and YA are the same side. So I'm not going to say no. But me, I'm always worried I'm going to mess it up. So I always try to go in the same order. But both would be acceptable. But if I was writing this one down, I probably would have written YA. What about angle? What is congruent with angle Y? Angle P. Angle K.
A,
Angle A. Here they're getting sneaky with us. Angle ACY.
K, P, M,
Almost. KMP.
M.
What about congruent to triangle MPK? CYA? What about triangle YAC? PKM. So again, not challenging in the sense that we're trying to set up an equation and then solve it or anything, like we've done so far. It's really just a visual exercise, making sure you pair things up consistent. Any questions so far on just some of the kind of the basics of congruency involving triangles? So now we're going to get into some of the main focus for today. There is actually a way to prove that two triangles are congruent without knowing that all the parts are congruent, which is basically what this statement here at the top says. If all corresponding angles and sides of two triangles are congruent, then the triangles are congruent. But I'm going to highlight, however, you can prove triangles are congruent using even fewer parts. So you may not know something about all of them, but there's a handful of special cases that allows you to prove that they are in fact congruent. And we're covering two of those today. We're covering side, 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 which I'll explain in just a moment, usually abbreviated with SSS. And then we're also going to look at side angle side, which is SAS. So the first one we're going to look at is SSS, side, 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 which states, this is just a statement, a factual statement. If three sides of one triangle are congruent to three sides of another triangle, then the triangles are congruent. So you don't even have to know anything about their angles, which hopefully shouldn't shock us too much, because last unit we said that the angle with its opposite side has a very unique relationship. Grow the angle, you lengthen the side. So because of that unique relationship, so long as the sides are all congruent, then all the angles inside must also be congruent respectively. So in the case of this diagram here, it's basically saying if AB is congruent to side DE, BC is congruent to EF, and then CA is congruent to FD. So long as that is either given or you can state that it is true with a little bit of proof, then it is safe to say that those two triangles must themselves be congruent. So triangle ABC is congruent to triangle DEF. And at no point did I state anything about the angles.
Doesn't matter if we put an AC or it has to be C.
If you put AC, hopefully you matched it with DF, then that's fine. Now, technically, I could say CA and DF are congruent, then I run into an issue where maybe I'm accidentally thinking C is paired with D. So I just want to be careful. Yeah, I'm not going to be that picky. That does make me realize though, as I build the test for this unit, I'm going to have to try to consider multiple scenarios just because you can mix them up, or I'll have to just go through and I'll figure out a way to do it. But yes, there is some variability there. And if you're not sure whether or not you're right, then just come check with me and I can take a look at it. All right, so what we're going to do for the next 1, 2, 3 is I'm going to do 2 things. We're going to practice thinking in terms of side congruence, but we're also going to introduce kind of a layout that is writing a proof. So the first 2 you'll notice the left-hand column is filled in for us. The right-hand column, the reasoning behind it, that's up to us to determine. But then the third one, we're all on our own. We're going to have to write the statements and then support them based off of what we see in the diagram or the information we were given. So I'm going to try to keep all of it up there on the screen. I want to make sure you guys can see as much of it as possible without cutting off too much. But here is an example of a proof that is only halfway done. So it says, given that side PQ is congruent to side ST, QR is congruent to side RT, and R is the midpoint of PS, we have to prove without any doubt that triangle PQR is in fact congruent to triangle STR. Now, personal recommendation, when I am given some facts like this here, I like to first go to my diagram because I'm a very visual person. And I like to sketch in some things just so I can visually see what's being verbally stated. So in this case, it tells me that PQ is congruent to ST. So I'm going to put a little hash mark on PQ, put a little hash mark on ST. It also tells me that QR and RT are congruent. So I'm going to put a double hash mark on those 2. And then it tells me that R is the midpoint of PS. And I'm not going to mark anything other than a point right there for now until we get to the statement that that corresponds with. So these are kind of exciting. I think they're kind of exciting. I used to hate them, but then the more I thought about it, I was like, oh, this is kind of, it's a nice little friendly debate with a piece of paper. So first statement that's already been given to us is that PQ is congruent to ST. How do we know that's true? I like, this is my first favorite question. How do I know that's true?
I mean, from what you just put up there, but that we don't know for sure. If you know
So we have to defend it. You pointed at it, I think. Wasn't it given?
Yeah.
So we have to, anytime it's in the given line, we have to believe it. Pictures we have to be a bit more careful on, but if we are told point blank, this is what it is, that's reason enough. So I'm going to say that that statement is true because it was given. What about QR is congruent to RT? How do I know that's true? It was also given. R is the midpoint of PS, also given. In fact, you're going to start to notice that usually you're going to restate the given information first before you start to then come up with some additional statements, which gets us to our fourth statement. PR is congruent to RS. Now that was not given, but how can we support that statement? And what does a midpoint do? Bisects, or in other words, cuts in half which means the two sides are equal. So I can then, based off of that statement, come up to my triangle and put 3 hash marks on those two parts. And the reasoning, just to kind of summarize it down, is that's based off of the definition of midpoint, right? You defended it because you told me it was a midpoint. So I would say definition of midpoint. And that proves it. That is the reason why we can say that statement and someone can't argue with us. We're trying to shut down any argument. If someone was to come in and say, well, that's not true, you say, well, sorry, I proved it. So then we get to the last statement that says triangle PQR is congruent to STR. And you'll notice the last statement will typically be the statement you're trying to prove. How do I know that they are in fact congruent? Sorry? All 3 sides are congruent. So specifically, we would say this is due to side, side, side congruence. Now, if someone says, I don't know what that means, you would say, well, just look here at this diagram up above. If all corresponding sides are congruent, then we can say that the triangles must be congruent. And we proved it. No one can come in and argue with that because we very, very specifically defended it. And it almost feels like we're not doing any math, which some may find refreshing. Others may be like, I'd rather just solve an equation. There are 2 types of people in the world, but this is an important thing to practice. Any questions on this one? Let's try the next one. Again, kind of leading us in the same direction, but here it is given to us that JL is congruent to MN and that K is the midpoint of JN and LM. So I'm going to go to my diagram here. JL and MN are congruent. So I'll put a little hash mark there. And then it's talking about K being a midpoint, which we'll get to that probably here in just a moment. I'm just going to put a point there just so it's, if it was important enough to state as a given statement, then it's probably going to serve a purpose here shortly. But I don't want to get ahead of myself. So I'm going to come down to my proof table. The first statement is that JL is congruent to MN. And what? Sorry?
Given.
It was given. Can't argue with it if it was already stated. Then the second statement is that K is the midpoint of JN and LM.
Given.
Also given. Now the third statement is that JK is congruent to KN.
Not given.
Definition of midpoint, because the K is the midpoint of JN, which means this was cut in half, making those 2 parts congruent. So we would say that we can defend that statement based off of the definition, I'm going to abbreviate, of midpoint. The fourth statement is that LK is congruent to KM.
Definition of midpoint.
Also definition of midpoint, because the midpoint is operating as a midpoint on 2 different segments. Okay. So then the last statement, which is what we're trying to prove, is that triangle JKL is congruent to triangle NKM. SSS congruence, side, side, side congruence. Because either we were given congruent sides or we proved that there were additional congruent sides, but when it was all said and done, we were able to pair all 3 sides together. Done. No one can come in here and argue with that now, because we very clearly defended every statement that we made. Okay. So moving on to number 3. A little scary at first because now it's up to us, but maybe we're starting to see some of the flow. So it's been given to us that AC is congruent to AD. So I'm going to sketch that on my graph or my diagram. It's also been told that CB is congruent to BD. So I'm going to double hash mark that up. What do you think my first statement could be?
AC is congruent to AD.
And how do you know that?
Is it stated?
It was stated or it was given. So AC is congruent to AD. And we can defend that by saying that it was given. What do you think your second statement could be?
C is congruent to AD.
And why is that? Also given. CB is congruent to BD. Now, here's where we kind of have to think for ourselves. We've restated all the given information, but then I need to think about it as I'm trying to prove that these triangles are congruent. I already have 2 of the 3 sides. I need to come up with a statement that the third side is congruent. Now, this one is a slightly unique diagram. But what can you guys tell me? What can you look at that diagram and tell me is true?
B is the midpoint between C and D
Ooh, how do you know that?
because it cuts it off.
Well, the only problem with that is that CD isn't a segment. It's got a bend.
I'm sorry. Would it be A, B, the midpoint, or because of the line?
Well, okay, so we're stuck with midpoint because we've used it twice now. But we don't want to get tunnel vision. Let me ask you this. We have 2 triangles right now. And I know that AC, so AC is congruent to AD, and CB is congruent to DB or BD. The third side I haven't looked at for either triangle is AB, which, because of how they're drawn, they both have the same side, right? Now let me ask you this. Can I then say that AB is congruent to AB? I could say BA, but they're the same side, right? And if I looked at my diagram, that would mean I would squeeze in there 3 little hash marks. But that's a true statement, right? Because of course it is, because it's equal to itself. Now, there is a property which we haven't talked about, but I'm going to mention it here, and we're going to use it probably a handful of times today and then some more tomorrow. This is actually known as a property called the reflexive property. And I'm very, very crudely going to tell you what that means by saying things equal themselves. We throw it back to algebra. 5 always equals 5. X always equals X. Something, I'm always equal to myself. I am me. So in geometry, we can say that if it's the same segment, it is equal to itself because it is what it is. Now, what that means though is we now have 3 congruent sets of sides is that enough then to say that these two triangles are congruent? Sure, because if you have three sets of congruent sides, that's right up side, side, side congruence. So I then can say my final statement, which is what I was trying to prove, that triangle ABC is congruent to triangle ABD based off of side, side, side congruence. That one was kind of a sneaky one. But think of it this way, it's meant to try to get you thinking outside the box. You have the information you need in front of you. It's training our mind to interpret what we're actually seeing. It'll get there. We'll get there. So those were three examples of not only proofs, but using proofs and side, side, side congruence to reach our final goal. Like I said, we're covering two types of congruence today, side, 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 and the second one for today is side, angle, side, which states that if two sides and the included angle, meaning the angle that is between those two congruent sides, so congruent, congruent, and then the angle here in the middle is congruent as well, of one triangle is congruent to two sides and the included angle of another triangle, then it is safe to say that the two triangles are in fact congruent. So here we have a diagram of two triangles. And if you look at it, you'll notice that we have a congruent set of sides, a second congruent set of sides, and then we have a congruent angle, which is between its two legs, so to speak, is made up of those two sets of congruent sides. Now, if you notice, that's why it's called side, angle, side. Angle is between the two sides. Oh, I should read my own notes. Included means the angle between the sides. So using the diagram just to kind of solidify this statement, if we know to be true, let me zoom in here just a hair. If we know that AB is congruent to DE, angle B is congruent to angle E, and that BC is congruent to EF, based off of side, angle, side congruence, based off of this statement, we have enough information to defend the statement that triangle ABC is congruent to triangle DEF. Now, on these last, I think, 4 proofs, we're lucky. The statements have been given to us because some of the reasons are a little bit extra based off of what's being said. But I promise you, we have enough information that we're going to be able to defend each statement as we go through this. So we're going to start here on the first one. These are sample side, angle, side proofs. So odds are every proof is going to result in 2 sets of congruent sides and a congruent angle in between. Kind of leave that in the back burner. Here, though, we've been given a diagram. We have been told that JM is congruent to NL. So JM and NL. And we've also been told that angle JMN, which is right here, is congruent to LNM, which is right here. So in our proof, you'll notice then that the first two statements just came from our given information. So I'll go ahead and write given and given. Now, the third statement says that MN is congruent to MN. Well, that shouldn't shock us too much because, of course, it equals itself. And if you refer back to earlier, that was that property we referred to as the reflexive property. Things equal themselves. But when I look at the diagram here, hopefully I'm not too terribly shocked that this was where the focus was at. Because if you notice, in this upper triangle here, we have we have one of the congruent sides, angle, and a congruent side. Whereas over here, we have one of those corresponding congruent sides, angle, side. Of course, we wanted to focus on this one in the middle, because had I done ML and JN, which I don't have enough information to support anyways, I would have had angle, side, side, which would just make an ass out of us. Yay, geometry humor. There is no ass congruence. So pay attention to the location. I'm gonna post this notes on YouTube and they're gonna flag me now, but so we're given the statement, then the proof statement that we're trying to prove this whole time. Triangle JMN is congruent to triangle LNM based off of what? SAS congruence, side, angle, side congruence. And that is because we had either given to us or we then followed it up with something we could visually see, prove that there were two sets of congruent sides and the angle included between them was also congruent as well. Number 5, we're given AB is congruent to BC. So I'm going to sketch a little hash mark over here. And that BD bisects angle ABC. Okay. We'll talk about what that means in just a moment. I'm actually going to highlight that though. Bisects, that's probably going to be important here. We're trying to prove that triangle ABD is congruent to triangle CBD. Hopefully you'll notice though, the first two statements yet again are given. Just restating what we already know. The third statement though claims that triangle ABD, which if I go to my diagram right here, ABD is right here, is congruent to angle CBD, which is right here. Well, how can I defend that statement? Not yet. Not quite. Because we only have one set of congruent sides. We're stating that we have a set of congruent angles, but we still don't have that second side. So we're not quite ready for side angle side yet. But how can I defend that those two are in fact congruent? I'll give you a clue. Look at what's been stated before. It wasn't specifically given, but Shanitha, what'd you say? What bisects? BD bisects angle ABC. What does the word bisect mean? So this angle is cut in half, which means these two little slivers in here of angles are two equal halves. Now, the way we could word this reason is we could simply say that this is thanks to the definition of bisect. So since BD is bisecting angle ABC, the two little half angles that are created as a result must then be congruent. Fourth statement says that BD is congruent to BD. That's the reflexive property. And then it seems that we have enough to support that triangle ABD is congruent to triangle CBD. Do we have enough for side angle side? I think so. If I look at my diagram again, side, angle, side, side, angle, side. Sure do. We have enough to say that this is in fact true thanks to side, angle, side congruence. I enjoy these, but I also understand that I'm kind of unique in that regards. So if you're not enjoying these, no offense, none taken. Number 6. Number 6 says that V is the midpoint of WZ and XY. And that is literally all it gave us besides the actual diagram itself. So only have one given statement. Now this is rather powerful though, because it is going to give me some information. Because the second statement is that WV is congruent to VZ. Why is that true?
Can we say it's the midpoint?
Because, well, we don't have to say it's the midpoint. It's already been said. So thanks to the definition of midpoint, that would be enough of a defense for that statement. Now the third one, this one's rather sly. Says that angle WVX, which is right here, is congruent to angle YVZ, which is right here. Curious, what's the defense of that statement? It's been stated, can we defend it? If it helps, it does require you to throw back all the way to unit 1 and different types of angle pair relationships. Oh, I think I heard it. They are vertical angles, and vertical angles are always congruent. So simply by saying that these are vertical angles, that is enough to defend why we can say they're congruent. I told you vertical angles are just going to keep creeping their way into a lot of our lessons. Fourth statement, XV is congruent to VY. Definition of midpoint again, because that V was not just the midpoint of WZ, it was also midpoint of XY. Now that we've defended all these statements, do I have two congruent sets of sides and the included angle as being congruent? Sure do. So then I have enough to say that these triangles are in fact congruent thanks to side angle side congruence. Last one for today, and I would say that it's probably the fastest we've gone through a set of notes, which is pretty cool. It's been given to us that HI is congruent to GJ, HI and GJ. But we're also told that HI and GJ are parallel. So one of the ways that's been denoted in the past is with one of these sets of arrows. So they're not only congruent, they are also parallel. So you'll probably notice the same thing for today. The first two statements are just both given statements. But then it throws at me that angle GJH, which is right here, is congruent to angle IHJ, which is right there. Sorry, I realized the diagram was really small when I marked those. How do I know that's true? It does throw us back to unit 1 again. And no, they're not vertical, but we're in the same thought process. Sorry? They are alternate interior. If you were to imagine, I know it's hard to see past two triangles side by side, but if you were to imagine with me real quick that HI was just going on forever, GJ was going on forever, HJ then is a transversal intersecting two parallel lines. Well, that gave us all sorts of special relationships: alternate exterior, alternate interior, consecutive, corresponding, all sorts of relationships. Just so happens though that GJH and IHJ are alternate interior. And so long as it's between two parallel lines, alternate interior angles are always congruent. So my reasoning for that statement is that they are alternate interior angles. Now, if you were to abbreviate that with like alt int angles, that's fine too. Just so long as you remember what it is that you were saying, I should be able to decipher it. Then it says HJ is congruent to HJ.
Reflexive property.
That is the reflexive property. You are correct. Now, if I look at my diagram, because I've kind of labeled it as I went, do I have two congruent pairs of sides and the angle that's included congruent as well? Sure. So I have enough for side, angle, side congruence. Cool. So a couple quick last minute statements before I pass out your worksheet. We only covered two types of congruence today for the proofs, which I believe you only have two proofs to do. The rest is kind of picking through some of that information like at the beginning of our notes today, making sure that your eyes are adjusting to see how congruent triangles relate and have their corresponding parts congruent. Tomorrow, we're going to add to that, my memory's crap, angle, side, angle congruence, angle, angle, side congruence, and then we're going to throw in kind of an oddball one called hypotenuse leg, which is unique to right triangles. We won't have as many of those, especially when it comes for the test time, but that is technically one situation where you have enough information. But yeah, for today, all you need to worry about is side, 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 angle, side. All right.